Triton, one of Neptune's most intriguing moons, holds a special place in the exploration of the outer solar system. This icy satellite, named after a Greek sea god, is unlike any other moon orbiting the planets of our solar system. With its strange retrograde motion, mysterious surface features, and potential for geological activity, Triton has become a fascinating subject for scientists trying to uncover the secrets of distant worlds beyond Earth. Triton was first discovered in 1846 by the British astronomer William Lassell. This discovery was remarkable because it relied on mathematical calculations rather than direct observation, a necessity given the limitations of telescopes at the time. Lassell's work not only confirmed the existence of Titan, but also sparked interest in its peculiar characteristics. Compared to Neptune's other satellites, Triton immediately stood out. Most of Neptune's moons are relatively small and move in the same direction as the planet's rotation. Triton, however, does the opposite, traveling in a retrograde orbit, which means it orbits Neptune in the opposite direction of the planet's spin. This motion is rare and suggests a unique origin for the moon. Furthermore, Titan shares many features with Pluto, the dwarf planet located in the Kuiper Belt. Their similar sizes, surface compositions, and overall structure hint that Triton may not have formed around Neptune, but was instead captured by the planet's gravity long ago. At 1,680 miles in diameter, Triton is Neptune's largest moon and far exceeds the size of its next largest satellite, Proteus. This size allows Triton to maintain a thin atmosphere primarily made up of nitrogen, with trace amounts of methane. Although the atmosphere is faint compared to Earth's, it plays a crucial role in shaping Triton's surface and potentially supporting its geological activity. Triton also has an ionosphere, a region where particles in the atmosphere are ionized by solar and cosmic radiation, which is more pronounced than Earth's, despite the moon's distance from the sun. Scientists believe this ionosphere, combined with the moon's unique surface features, offers clues about its internal composition and activity. Triton's structure is thought to include a rocky core, a liquid mantle, and a crust made primarily of ice, giving it an intriguing similarity to Earth's own layered composition. One of Triton's most striking features is its extreme cold. The average surface temperature hovers around -400 degrees Fahrenheit, making it one of the coldest places in the solar system. This frigid environment is due to its great distance from the sun, about 2.8 billion miles away. The surface is covered in frozen nitrogen, giving Triton a bright, reflective appearance. Despite the cold, Triton's surface appears surprisingly young, suggesting ongoing geological processes. Large regions of the moon are smooth, with relatively few impact craters, indicating that its surface has been reshaped over time. This contrasts with other moons in the solar system, where older surfaces are pockmarked with craters from meteor impacts. Triton, Neptune's largest moon, is known for its unique surface features, including a melon skin texture with large ridges and valleys. Black streaks mark parts of the surface, likely caused by cryovolcanic activity, where subsurface materials like water or nitrogen erupt onto the surface. This cryovolcanism, driven by tidal forces from Neptune's gravity, generates internal heat, causing ice to melt and surface materials to rise. The resulting surface rejuvenation keeps Triton geologically active despite its icy exterior. Its highly reflective icy surface, which bounces back about 70% of the sunlight, suggests the possibility of an internal ocean beneath its frozen crust. Additionally, nitrogen geysers, first seen as dark streaks, shoot particulates into Triton's thin atmosphere, hinting at active subsurface processes. These features indicate that Triton is not a lifeless world, but one with ongoing geological activity. Despite its frozen temperatures and distance from the sun, scientists hypothesize that beneath Triton's frozen surface lies a subsurface ocean. This liquid layer, possibly made of water mixed with other substances like ammonia, could be kept warm by tidal heating. Tidal heating happens because of the immense gravitational forces Neptune exerts on Triton, constantly flexing and stretching the moon's interior. This movement generates heat, melting parts of the icy crust and creating pockets of liquid underneath. The existence of this ocean is a tantalizing idea because liquid water is a key ingredient for life as we know it. If Triton's ocean's real, it might harbor conditions suitable for some form of life, even in its cold, remote environment. Our understanding of Triton grew immensely thanks to the Voyager 2 spacecraft, which flew past Neptune and its moons in 1989. This was the first time humanity got a close look at Triton, and the data it sent back was groundbreaking. Voyager 2 captured detailed images that revealed Titan's bright, reflective surface and its unusual geological features, including smooth plains, ridges, and valleys. It also measured the moon's thin nitrogen atmosphere and confirmed its retrograde orbit. The mission provided the first estimates of Triton's mass and density, suggesting it was a captured object, possibly originating from the Kuiper Belt. However, Voyager 2 could only observe about 40% of Triton's surface during its flyby, leaving much of the moon unexplored and raising more questions than answers. In recent years, new observations of Triton have reignited interest in the distant moon. The James Webb Space Telescope has provided updated images and data, offering fresh insights into its surface and atmosphere. Triton's highly reflective surface, covered in nitrogen ice, shows seasonal changes in temperature. These seasonal variations might drive changes in the thin atmosphere, causing shifts in the pressure or even temporary bursts of activity, like geysers. These findings suggest that Triton's surface is more dynamic than previously thought, adding to its allure as a target for future missions. Some scientists have speculated that these seasonal changes might reveal clues about Triton's potential for supporting life, as even small shifts in temperature could influence any subsurface ocean. Titan's retrograde orbit, one of its most peculiar characteristics, also hints at its mysterious past. Most moons in the solar system orbit their planets in the same direction as the planet's rotation, but Triton does the opposite. This retrograde motion is so unusual that it almost certainly means Triton wasn't originally a part of Neptune's system. Scientists believe it was captured by Neptune's gravity billions of years ago. Triton has similarities to Pluto, such as its size, density, and surface composition. This supports the idea that it might have originated in the Kuiper Belt, a region of icy bodies around Neptune. Its capture likely disrupted Neptune's existing moons, ejecting some from the system and reshaping the orbits of others. Triton's origins might also shed light on double planetary systems like Pluto and Charon. Before its capture, Triton might have been a part of a binary system, with two similar-sized bodies orbiting each other. The gravitational interaction with Neptune could have torn the pair apart, leaving Triton trapped in orbit around the planet. This theory not only explains Triton's retrograde motion, but also highlights how dynamic and chaotic the early solar system must have been. Triton's unique characteristics, like its geological activity, potential subsurface ocean, and puzzling origin, make it one of the most fascinating objects in our solar system. With advancements in technology and new telescopes like the James Webb, we're closer than ever to unlocking its secrets. Triton could be the key to understanding more about icy moons, planetary formation, and even the possibilities for life in the outer reaches of our solar system. Triton's a place that sparks imagination about the possibility of life beyond Earth. Scientists are intrigued by its potential because it appears to have some of the essential ingredients for life as we understand it. The presence of water is a critical factor. Triton's icy crust could hide a subsurface ocean warmed by tidal heating, creating a liquid environment despite the moon's distance from the sun. Liquid water is vital because it provides a medium for chemical reactions that are necessary for life to begin and thrive. Titan's surface and composition also suggest the presence of carbon-rich materials, another key ingredient for life. Organic molecules made up of carbon, hydrogen, and other elements are considered building blocks for living organisms. These materials could be delivered to Triton by comets, or could have formed during its early history. However, even with water and organic compounds, Triton faces significant challenges when it comes to supporting life. Its extreme cold, with surface temperatures around -400 degrees Fahrenheit, and its thin nitrogen atmosphere create a harsh environment where life as we know it would struggle to survive. One factor that keeps the possibility alive is the seasonal warming that occurs on Triton. As Neptune completes its 165-year orbit around the Sun, different parts of Triton's surface receive varying amounts of sunlight. During these seasonal changes, the surface temperature can rise slightly, causing shifts in the thin atmosphere and possibly triggering temporary bursts of activity. These warmer periods might briefly create conditions more favorable for chemical reactions or for the transport of materials between the surface and the subsurface ocean. While it's a long shot, such changes could influence the moon's potential for harboring microbial life deep below its icy shelf. The mysteries of Triton have captured the attention of scientists and space agencies, leading to plans for future exploration. One of the most exciting proposals is NASA's Triton mission. If approved, this mission would send a spacecraft to fly by Triton and study its surface, atmosphere, and potential subsurface ocean. Triton aims to provide answers to key questions about Triton's geology and its ability to support life. It would use advanced instruments to map the surface in detail, analyze the thin atmosphere, and look for signs of cryovolcanism and other active processes. China has also expressed interest in exploring Triton as part of its broader plans to study Neptune and its moons. A nuclear-powered spacecraft has been proposed, which could provide the energy needed to study Triton's cold and distant environment for an extended period. Missions like these are crucial because they focus on ocean worlds, a category that includes Triton, Europa, and Enceladus. These icy moons are considered some of the best places to look for life in the solar system due to their potential for liquid water and active geology. Studying Triton isn't just about searching for life. It's also about understanding the origins of life itself. By examining how water, heat, and organic materials interact in extreme environments, scientists hope to learn more about the conditions that could have led to life on Earth and elsewhere. Triton, with its unique characteristics, could provide insights that extend far beyond Neptune's orbit. Its geological activity and retrograde orbit could also offer clues about the dynamic processes that shaped the solar system billions of years ago. The future missions will not only help solve the mysteries of the distant moon, but will also deepen our understanding of how life might arise in the universe. Triton's story is one of curiosity and discovery, and its secrets may one day help answer some of humanity's most profound questions. Well, that was it for today. Don't forget to subscribe to the channel. If you're interested in knowing more about the planets, watch our video on what did we find in the first real images of Neptune. See you in the next one. Bye.